Welcome to The Explainer. I'm so thrilled you're joining us today. If you've ever looked at a calculus textbook and felt just a massive wave of dread wash over you, you are absolutely in the right place. Today, we're going to take some of the most famously intimidating mathematical concepts in the world and translate them into simple, everyday language. We're going to completely demystify calculus, and we're going to do it relying on nothing more than toy cars, pizzas, and train stations. All right, let's dive right in. So let's just plunge right into our central mystery. Imagine a little car traveling down the road from point A to point B. Suppose the whole journey is 100 kilometers, and it takes exactly 2 hours. We can all do the easy math here, right? 100 divided by 2 is 50. So the car's average speed is 50 kilometers per hour. Simple. But now I want to ask you a much harder question. How fast was that car moving at exactly 1 hour, 17 minutes, and 32 seconds? The answer isn't necessarily 50. Maybe the car was speeding up to 70 or slowing down to 20. Or maybe it was literally at 0 because it was stopped at a red light. So how on earth do we measure speed at one exact frozen instant in time?
And honestly, this hits the nail right on the head for the paradox we're dealing with. Average speed is incredibly straightforward because it tells us about a whole journey. You take the total distance, you divide it by the total time. But instantaneous speed, like speed right this second, mathematically, speed requires a change in time. If we freeze time to ask how fast we're going at one exact second, absolutely no time is passing. 0 time. And as we all know, you can't divide distance by 0. To solve this impossible puzzle, we're gonna need a brand new mathematical tool. We need to enter the world of limits.
Section 1. The art of approaching. Visualizing how numbers get closer. Before we can solve our car mystery, we have to build up our conceptual toolkit. Think of walking toward a destination. If you take a step closer, then another step, you're approaching your destination. That's the core intuitive idea of a limit. Let's visualize how numbers actually do this. Imagine we start with a number 1. Then we add a half, bringing our total to 1.5. Next, we add a quarter, taking us to 1.75, then an eighth, taking us to 1.875, and so on. Every single new piece we add is exactly half the size of the previous one. Notice how the error, or the distance from the number 2, keeps shrinking. It goes from 1 down to 0.5, down to 0.25. We're adding tinier and tinier fractions, and the total is continuously inching forward. Everything we just stepped through was creeping toward one ultimate destination, and that is the number 2. In mathematics, we say that this sequence approaches 2, making 2 the limit. But listen, here is one of the most absolutely crucial things you need to understand. None of those partial sums we just calculated ever actually equal 2. They are only getting closer. Approach doesn't necessarily mean arrive. Imagine you're a child walking toward your mom. You can keep getting closer and closer without ever discussing whether you actually reach out and touch her. A limit simply describes the destination. It just cares about answering one question. How close can you get? Let's look at another really cool way to visualize this. Picture a perfect circle. Now let's put a shape inside it, a polygon. Step 1, we start with a square. The square's area is clearly way less than the circle's area, right? Step 2, we use a hexagon, which has more sides and fills up a lot more space. Now step 3, imagine a polygon with 1,000 sides, or 1,000,000 sides. As the number of sides increases infinitely, those straight edges become so totally microscopic that the shape becomes more and more circle-like. The polygon's area gets closer and closer to the true circle's area. It's kind of like cutting a pizza into millions of incredibly thin slices. Eventually, the difference between the polygon and the perfect circle becomes practically 0. Section 2. The limit game. Meet epsilon and the ultimate mathematical challenge. Okay, so we know what it means to approach something, but in math we've got to be rigorous. We have to prove exactly how close we can get. To do that, we play a little game. Imagine I'm a teacher and you're a moving variable. I draw an invisible circle around our destination, let's say the number 2 again. I issue a challenge. Get within 1 of 2. You do it. Easy. Then I say get within 0.1. A bit harder, but you do it. Then I demand you get within 0.000000001. Very, very tiny. The symbol mathematics uses for this requested microscopic distance is epsilon. Think of epsilon as this invisible microscopic measuring ruler. As the teacher, I choose how close you have to get, and I keep making the challenge harder. A true mathematical limit must pass every single one of these epsilon challenges. No matter how impossibly tiny, I make the allowed distance. Section 3. The rule of staying. The train station paradox.
You know, passing that epsilon challenge is super impressive, but it's actually not quite enough. There's one more major rule in our conceptual toolkit, and it's the one textbooks really want you to notice. What happens when something gets incredibly close to a destination but completely fails to remain there? Imagine a train zooming toward a station. It approaches the station. It gets 10 meters away, then 1 meter, then 0.1 meters. It looks fantastic. It's getting extremely close. But then, it just blows right past it. It zooms straight through the station and continues down the track, moving 1 meter away, then 10 meters away. Can we say the station is the train's limit? No way. We absolutely cannot. Why? Because the train got close, but it didn't stay close.
So, here is your crucial takeaway. A limit means a variable gets arbitrarily close to a destination and stays arbitrarily close. The word remains is literally the absolute heart of this definition. If the numbers start bouncing away again, just like our runaway train, there is no limit. Now, because of all these strict rules about epsilon challenges and staying close, math textbooks are going to hit you with a notoriously scary formal definition. It usually reads something like this. A is the limit of x if the difference between x and a becomes and remains smaller than any positive quantity we choose. Wow. If you read that in a classroom, it sounds totally terrifying, doesn't it? It's thick, it's dense, and it's incredibly intimidating.
But hey, we can translate that exact same terrifying definition into a simple, everyday child version. All it actually means is this. Pick any tiny distance you want. The moving number eventually gets inside that tiny distance from its destination and stays there. That's the whole shebang. Math really doesn't have to be a nightmare of jargon. We literally just conquered the formal definition of a limit using nothing but common sense.
Section 4, zooming in for the answer. Solving the impossible car problem. Okay, we've got our toolkit. We know how limits work. It is finally time to bring it all back to our original mystery and crack the case of instantaneous speed. Remember, we couldn't measure speed precisely at 1 hour, 17 minutes, and 32 seconds because zero time was passing. So how do limits save us here? Let's see how this builds using a camera zoom analogy. Instead of looking at zero time, let's just look at a really small piece of time. Step 1, we measure the car's movement during a 1-second interval. Say it moves 10 meters, making its average speed 10 meters per second. But that's still an average over a whole second, right? So step 2, we zoom in to a 0.1 second interval. Step 3, extreme zoom to a 0.001 second interval. If you look at a whole hour, a car's speed can change wildly. But if you look at a microscopic fraction of a second, the car has almost absolutely no time to change its speed. And here is the incredible aha moment. As we make that time interval smaller and smaller and smaller, the average speed over that tiny interval gets closer and closer to the actual speed at that exact moment. We simply watch what number the average speed is approaching as the time interval shrinks towards zero. It's a limit. The final destination that the average speed settles on, that is the instantaneous velocity. We solved it. We found the speed right now just by zooming in infinitely close. And honestly, this completely demystifies one of the scariest formulas in all of calculus. You might see this written on a chalkboard: V equals the limit as delta t approaches zero of delta s over delta t. Don't panic. Delta s is just a small change in position. Delta t is a small change in time. The formula just says exactly what we just did. Take the distance traveled, divide it by the time taken, and make that time interval shrink towards zero. Zoom in on time until the speed settles. That is literally all calculus is doing here. As we wrap up these concepts, I want you to remember these 3 golden phrases. This is your core takeaway for understanding limits. Number 1, get close. The variable approaches the destination. Number 2, as close as we want. It has to pass that invisible, microscopic epsilon challenge. And number 3, stay close. It must remain within that boundary, unlike our runaway train. Get close as we want, stay close.
We've literally just crossed this beautiful, logical bridge right into calculus. We started out with basic distance and time. We moved to average speed over an hour. Then we looked at smaller time intervals like minutes and seconds. We applied our amazing new tool, the limit. That allowed us to find the instantaneous speed in a millisecond. And mathematically, that instantaneous rate of change is what we call the derivative. We just logically built the entire foundation of calculus completely from scratch. As we wrap up today, consider this. We used limits to find speed by shrinking a time interval infinitely close to zero.
But if instantaneous speed technically requires freezing time to absolute zero, are we ever truly moving in a single frozen instant? Or is motion just an illusion created by stringing countless frozen limits together? The sheer beauty of mathematics is that it gives us the rigorous tools to answer profound questions just like that. Thank you so much for joining me on The Explainer today, and keep exploring.